Hello students, it's Sunday morning and I'm going to be recording lectures that I've done in the past on Zoom. That way I can put them directly onto YouTube without having student information show up. This is the lecture on CPUs, which is really a lot of fun. So what I'm going to do is, let's go to screen share, and I'm going to share this. Okay, and let's stop share for a second. I'm going to do one more thing so I don't go through this again and make a boo-boo. And here it is. There you go. And I will go ahead and start with this now. So go to slideshow and from beginning. Now what I'm going to do is hit some of the highlights for microprocessors. There's a little bit more in the chapter. Be sure to read it, but here's the highlights you just got to know. Okay. Microprocessor has a ton of parts. Now, as we look at this, let me get my laser pointer in here. Has a huge amount of wires coming in. The wires come in through these pins at the bottom. They're gold plated. You notice it's a 30 by 30 grid, which means about 900 wires, which is a lot more than the 44 that I had when I started. These wires can put in a 1 or a 0, and that is the basis of a microprocessor. The current that comes in is all at, I believe, around 5 volts, maybe 3.3, depending upon the technology. And when you send a slight blip of current, a sine wave, if you will, to the solid state, it turns a current on or off. Now, they do this when there is a clock cycle, when we get a pulse from one wire that says, quick, read the registers. Ooh, what's a register? We'll find out in a second. The clocks that allow you to have these things read are very fast, and they've gone from a speed of about 1 million. Now, how do you get information into that box? Now think about it. You saw the back side, which was 900 wires. Well, how does that work? Well, you plug it into a motherboard. The motherboard has the crystal. The crystal has the clock that will send in the pulse. Then within, you're going to have something called a register. The register was developed when they found out, well, how do I communicate with the CPU? It was like a black box. How do you get information in? Well, the way they got around it, the man in the box, was to put in lights on the outside, so to speak. This is the concept. And then on the inside is the same thing. So if you have a light on the outside, it's also inside the box is on. So they're identical. And in that way, by supplying information to the external data bus, you can send information to the registers, which are part of the microprocessor. And it was eloquent. So if it's on here, it's on there. So instead of just having 8 lights, we have several banks of these registers, and they're labeled AX through BX. And these registers then have multiple combinations. If you take just one, let's say 1 times 2, or 1 to the power of 2 is 1, and 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 10, 24, 40, 96, 8, almost 9,000 combinations. And I've only gone through 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 possible things. As I go up, they go up exponentially. So it gives you a huge amount of potential information going into the CPU. The CPU then takes these different combinations, and they are either a number, a letter, or a command. And it's just brute force simple. So this is called machine language. One command is a line of code, and the complete set of commands is called the instruction set. Big, big business when we were developing the new processors, which were the RISC and CISC, and going from 16 to 32-bit. Now, Cool thing about this is the CPU, it sees the lights, but it doesn't know when to read them. How would I know when the next instruction comes? Well, it's called a clock cycle. You basically send a sine wave through that one wire, and the computer basically says, oh, it's time to read the registers. Now, the faster it can read and the faster you can have these lights pop on is called the clock speed. So if you can read one set of registers, all the registers in 1 second, that would be 1 hertz. If you could do a million, okay, that's megahertz. A billion is gigahertz. So I went from thousands of hertz to gigahertz, almost a billion times as fast. Now, the old 8088 ran at 4.77 megahertz. Now they're running at gigahertz, plus multiple cores make it even faster. So how does this clock work? Well, basically it's a piece of quartz. The quartz is supplied with an electric current. The current makes it vibrate. Each vibration is 1 clock cycle. By precisely putting enough voltage in, you can get any speed you want. Now, on the chip, now this is an old one, 8088, 1978. My God, that's old. Here we have 8 wires for data, or the bus, and here's the clock. It only takes 1 wire. Then, okay, I'm reading the register, but where does the information come from? Well, it comes from your hard drive. But in the old days, the hard drives or floppy drives were very, very slow. So we would take the information and load it from the hard drive to what was called the memory, random access memory. Okay? So this memory has an address and you're able to get it. Now, today we're using what's called a DRAM, dynamic random access memory. In the old days, this took a huge amount of overhead because we'd have like 50, 60 chips, and it would take up half the motherboard. Also, it was most of the cost of the system. Nowadays, we put all the memory onto memory modules that are mounted vertically in the motherboard, and it seems to work great. Now, the only downside is these are fairly inexpensive, but they have to be refreshed constantly, meaning you have to have the electricity on, otherwise they lose the data. For instance, if you've ever been typing a paper, power goes out, where's my paper? Well, it's somewhere else. It's not on your computer anymore. Now, the address bus needs to communicate with the RAM, and it has a special chip that does that. It's called the MCC memory controller chip. Think of it this way. You've got the fastest connection, which is on the external data bus between the RAM and the CPU. And this chip enables it to happen very, very fast. Then the address bus is separate from everything else. When we look at motherboards, we'll see all these different traces, but here, everything has to, information comes through the address bus, so it's blazing fast. Now, the number of wires in the address bus determines the maximum amount of RAM the CPU can handle. The old chip that we looked at had 20 wires, okay, or 1,000,000 combinations. The new ones have 900 wires, and you're talking gigabits of information coming in. Here's an old chip. Intel and AMD, Motorola was in there, but they got blown out of the water by making bad decisions. Now, ways that they've improved CPUs, clock multipliers. The motherboard does not run as fast as the CPU, so the CPU is going to have a multiplier. Think of it as gears to allow it to go faster. 64-bit processing, so we have more wires going into the CPU, and we can do more processing. Virtualization support, we have a whole chapter on that, where we build a computer within a computer using digital techniques. We can execute instructions in parallel. We have multi-core processing. This is where we took one core and basically found that we could have 2 cores. They would be smaller, but the 2 of them would be larger than the single core. It's easier to manufacture the multiple cores and basically to wire them together It's called wire bonding within the package where the CPU is, and we can also add other stuff. An integrated memory controller also goes in that package, and a lot of CPUs have graphic processing ability. Although the big gaming systems will generally want their own video card so that it takes none of the power away from the CPU. And then security. Now, this is a rough area. We've been, seeing all kinds of attacks on our infrastructure, on our data, etc. And we're starting to hardwire security on the CPU. You can't override a hardwired CPU function. Now here's a picture of a CPU-Z, which is a diagnostic tool. And here it's showing me the core speed, okay, in terms of megahertz. So if it's running at 1,546, it's running at 1.5 gigahertz. Here it's got a multiplier of 15x. It has, let's see, the caches I talked about, L1 through L3, or I will talk about, and it has 8 cores. So, whoa, things cooking. Now, the EDB and address bus size have increased in size tremendously, and we've been using new technologies, and one of them was going from 32 to 64-bit. It's not going twice as much, it's going an order of magnitude. It's kind of like earthquakes. Each time you go from 7 to 8, it's not a little bit more powerful, it's exponentially more powerful. The 64-bit processing allowed us to use better software, faster. You could put more information in because it's traveling faster. And also, it allowed us to expand the amount of RAM we could use from 4 gigabytes of memory maximum for a 32-bit system to 16 exabytes for a 64-bit. Again, order of magnitude bigger. Now the cache. All right, the RAM, random access memory, was pretty good. However, it helped if we could have a little bit of memory closer to the CPU and preload instructions. So that's where L1 was born. Then we found out that we needed more, or another step, L2, L3, and now all those are in the package with the CPU. So you have tons of memory lined up, ready for the CPU to use, and these caches make sure that it's taken from the RAM and put into the CPU so there's no delay. All right, that's enough for right now.